Yeah, it's not only test 2, but we have a lecture after that, but I call the whole thing test 2. All right, so next thing, so given that we found this expected value given x, the next question was then to use this to find the expected value of u of x. And you know that given x equal 1, you have this expected value, and then you need to multiply it by the probability that x is 1 plus the value is 1 times probability that x is equal to 2, because this is when x is equal to 2. So you do that and you find that that expected value is 5/7, and it is exactly equal to the expected value of y that you found in the second question, which is supposed to be the case because the expected value of the expected value of x of y given x is supposed to be equal to the expected value of y. So these two answers are equal. If you don't find that they are equal, then perhaps your work is not correct. Now, question number 2. So in question number 2, I mean, this is exactly the problem we have on the homework, except that I transform just multiplying y by 2 there. So you know you need to integrate first with respect to x, and then with respect to y, and then with respect to x, so that you avoid having issues with the final answer you get. When you integrate with respect to y, you know that y is larger than x, so you're integrating from x to infinity, and then you integrate with respect to then you integrate with respect to x. Now, when you integrate with respect to y, you combine these two, that becomes t2 minus 2. So when you integrate, it goes to the denominator. You plug in x at infinity, you get 0 at infinity, and then you get this at x. Then you combine the two things again and you integrate. And instead of integrating by parts here, I'm just giving you another hint on this other problem. So when I want to integrate this, I think of the distributions that I'm using. I do a u substitution. So I substitute u equals 2 minus t1 minus t2 times x. du is going to be 2 minus t1 minus t2 dx. When I put them all inside here, t2, 2 minus t1 minus t2 square pops out as denominator, because dx is du over that, and x is u over this, so it's squared. And when they pop out, you see this integral now has no t in it. And in fact, I don't even need to compute that integral because this is a distribution, so the integral is equal to 1. Because the integral of a distribution is 1. Therefore, the moment generating function is equal to that under the condition that t1 plus t2 is less than 2 and t2 is less than 2. The first thing is to make sure you know that the definition of the moment generating function of a vector is equal to expected value of e to the t1 times the first component plus t2 times the second component. It's not just one t, there are two t's there. Now, to answer the second question, and of course, the first question was to avoid you having to compute integral. That's why the first question was there. To answer the second question, you don't need to compute two integrals to find the second moment and the first. You use the fact that the moment generating function of x is obtained when you put t2 equals 0. So when you plug t2 equals 0 into this formula, you find the moment generating function of x equal 4 over 2 minus t squared. Now all you need to do is take derivatives and plug in 0 to find the expected value. If I take the derivative, I get this. It's very simple to do. I get this. Plug in t equals 0, you get the mean of x. That gives you 1. And then you find the second derivative. Plug in t equal 0 again. You find the expected value. This is the expected value of x squared. And you use them in the formula of the variance, which is the second moment minus the square of the first moment. So that is 3/2 minus 1, which is 1/2. And if you are answering this question and you think I end up with a variance that is negative, you should know you are wrong, because the variance is always a positive number. Any questions? Yes.
Can you repeat how you got the moment generating function for just the x component?
Plug in 0 for t2. All right, next. Next thing we had was in question 3. And this was basically the question on moment generating functions that you had with the Poisson distribution. I just changed the distribution now to be normal. So you have x, y are independent. You know that x plus y follows normal with mean 5 and variance 16. And you know that x is standard normal. When x is standard normal, it means the distribution of n has mean 0 and variance 1. The moment generating function is given. The moment generating function of z is given, which is that. And then you know that because x and y are independent, the moment generating function of z is equal to the moment generating function of x times the moment generating function of y. And therefore, you can solve for the moment generating function of y to find that it is the ratio. And then you divide to get e to the 5t plus 15/2 t squared. And this, you can recognize this as the moment generating function of the normal distribution with mean 5 and variance 15. Now, question number 4. When we were doing this in class, I told you this is going to be on the test. So you have x, y, z, a vector x, y, z that follows normal 3 with mean a vector and variance matrix sigma. A is given as 1, -1, 0, which means this is the mean of x, this is the mean of y, and that's the mean of z. Then sigma is given as this. And this means this is the variance of x, this is the variance of y, that's the variance of z. This is the covariance of xy, this is the covariance of xz, that's the covariance of yz. That's what is inside the covariance matrix. Question, find the distribution of y1, y2, where y1 is x minus z, y2 is y plus z minus 1. So how do we do this? This is the kind of problem where you have vector y equals ax plus b. So you need to find a, find b, and do the work. In this problem, therefore, a would be what you multiply by this to get what is x minus z. So that's 1, 0, minus 1. And the second line would be to give you y plus z minus 1. So that is 1, 1, and then minus 1 for b. Therefore, you get the vector is equal to this times z, x, y, z plus 0, -1. And therefore, you know that y1, y2 will follow normal with two components with mean mu and variance sigma 1, where mu is equal to a times the mean of xyz plus 0, -1, which is the b. And you do that work, you find 1, -2. You don't keep it like that for me to compute for you. So you get 1, -2, and then sigma 1 is equal to a sigma a transpose. So you write that formula there, the matrix sigma from there, and the transpose of that, and then you multiply these matrices. When you do that, you obtain 7, 10, -4, -4. So y1, y2 follows normal 2 with mean 1, -1, and variance matrix 7, -4, -4, 10. That's it for the first part. Now, the second part of the question asks you to find the probability that x is between -3 and 5. X, not y1, not y2, but x. And the distribution of x is given in this matrix. X is normal with mean 1 and variance 4 given in the table. So that's the distribution that needs to be used to find the probability. So using that distribution, you form the z values, -3 - 1/2, less than 5 - 1/2, which gives you probability that z is between -2 and 2. You don't need a calculator for that, right? And so this is 1 minus 2 probability that z is less than -2. And that number in your table is the same as probability that z is larger than 2. It's 0.0228. 1 minus 2 times that gives you the answer, which is 0.95.
Dr. Longla, can you tell us again where you got the 1 and the 4 for x?
X, Y, Z follows normal with mean A and variance covariance matrix sigma. X is the first component of that vector, so the mean of X is the first component here, which is 1. The variance of X is the first component right there, which is 4. That's what stands in the variance covariance matrix. The diagonal is made of the variances, and the off-diagonal elements are the covariances, by definition.
Thank you.
So here you got 4 for X. If the question was Y, you would have mean -1 and variance 3. If it was Z, you would have mean 0 and variance 3.
So the distribution of y1 and y2 has nothing to do with.
Question B is not part of question A. It said X, not Y1, right? Not Y2. I understand your problem. Any other questions on this one? I didn't put Y1 or Y2 there because that would have penalized someone who got the first one wrong. Then he won't be able to answer the second one. That's not a good way of having a question. So the only thing there was to understand, if you remember, what the Z value is and how to use the Z table. Any other question on this one? Oh, and let's get to the last one. This is also one of the questions that we had on that homework. I just switched Poisson distribution to gamma. So, and I think we actually had another gamma too, right? It was a gamma exactly like this with 6 and 8. I just put the number, the constants instead of the numbers. So in general, if you have a gamma distribution with parameters A1 and C, another distribution with parameters A2 and D, and then if you switch the coefficients that you have inside and put as coefficients of X and Y, then the random variable that you obtain is also going to be a gamma. That's actually the theorem that I had you to prove in that question. So you switch, if you switch these coefficients and put them as coefficients of X and Y, the random variable that you obtain is also a gamma with coefficient that is going to be the product of the two coefficients and the sum of the first coefficients. How do you do that? The moment generating function is equal to mx of dt times my of ct because they are independent. And then you know the formula of m was you had your formula sheet, so you plug them in. Some people when doing this forgot that plugging in here, you're plugging in dt, not t. Plugging in ct, not c. When you plug that in and you compute, you can see it's c dt, so it's the same thing here. So it's 1 over 1 minus c dt to the power a1 plus a2, and you can see that this is also the moment generating function of gamma a1 plus a2 and cd. And one thing that I saw people having issues with is here, if you are to put the conditions, it's less than 1 over cd, not minimum of cd or maximum of cd, whatever. So it's the coefficient that is here that has to be the condition, right? Because when you have beta, you have t less than 1 over beta, right? So the beta of this distribution is CD. That's it. Any questions? All right, if no questions, then we wrap these topics and we move on to a new life. So your homework 6 has been there for a few days already, and it's due on Wednesday. So please make sure you do that.
It's due a week from today, not a week from the test.
I mean, you understand what it is, but we said it's due Wednesday, right? So I can just put it on Monday. But those who want to submit early can always do that. I will be happy to tell them what the issues are. So Wednesday, the material I think of that is almost fully covered. The rest of it is going to be covered today. And hopefully we do problems. So, okay. To avoid having certain things, I'm thinking about not wasting too much of your time here. This way. Is that better for those who are behind there? I'm trying to write everything up before coming here and show it to you like this and talk about that. I think it would be a lot better than writing and taking the time to put that down here. So the thing that we will be talking about today is the confidence interval for different setups that you can have. It's a continuation of the problem that we had last time, the statistical problem that consists of trying to have inference on a distribution that we don't know. We explained that there were two cases when you know absolutely nothing about the distribution, and the second case when you know the distribution up to a constant that is unknown, and your job is to estimate that constant and use it to decide what's going on with that population. So today we are continuing in the second setup. When you know the distribution up to a constant, and you want to decide what is going on with that constant using a sample that we call a random sample from the population. So now we have a population X that has a parameter theta. We have a random sample x1 up to xn from that distribution, and we need to use this sample to create an estimator defined as theta had in the previous lectures. And our goal is to estimate the error of the estimation, which means to have a measure of how off we can be by using our estimate, claiming that it is theta. Does that make sense? So when you estimate, you don't know theta, you take your population, you take a sample from it, you obtain an estimate, and the question is, how far is your estimate from the true value? And that's the question that we will answer today in various setups. So one way of answering that question is to build a confidence interval. A confidence interval that will tell you that with probability, maybe 95%, the true value theta that you're trying to estimate is going to be inside the interval that you build. Okay. And how do we build such an interval? So we assume alpha is given between 0 and 1. What is alpha? It's the level of confidence. Alpha is called the level of confidence. It's a number between 0 and 1. It is the maximal error you can afford. Okay, it should be a small number, usually less than 0.05, which means 5%. You want to be wrong at most 5% of the time. That's what it means. Okay, and we construct two statistics. You know, a function of the data is called a statistic. So you build two statistics, L and U, L for lower and U for upper, because you need a lower bound and an upper bound. So you build the two statistics and you say that LU, the interval LU, is a 1 minus alpha times the 100% confidence interval for theta if the probability for the true value to be inside that interval is 1 minus alpha. That's what I was saying in words earlier. So you have a 100 times 1 minus alpha % confidence interval if you can build U and L such that the chance for theta, which is the true value that you are trying to estimate, falls within that interval with probability 1 minus alpha. And that therefore means that not falling there will have probability alpha. That's the maximal error you can afford. Assume that you are a medical doctor and you have patients and you're using your history to predict whether the next patient that is coming to you is going to get some help using the treatment that you have been administering to other people, right? You want to decide that based on the symptoms that the person is giving you. You don't want the chances of getting the wrong outcome to be high, right? You want to make sure that the error that you can make is as small as possible. That's the alpha. Okay. And you want the chance for you to cure the person to be as large as possible. But you know that chance can never be 100% because there is no such medicine that 100% cures. Does that make sense? So that's the difference between the 1 minus alpha and the alpha. You want 1 minus alpha to be large. You want to be right as often as possible. That's it. When you solve a problem and then you find a probability of 0.0000, and then you start smiling, because that means that for you to be wrong, it's really, really rare. Right? But if you're doing it and then you find a probability of alpha being 10%, 15%, oh, that, man, you really need to check what you're doing. Right? All right, so this interval LU is called a 1 minus alpha times 100% confidence interval. And the number 1 minus alpha is called the confidence coefficient, while alpha is called the confidence level. Now, the thing that we can never answer those questions without is the following central limit theorem. I have my friend sitting behind me that probably is seeing that theorem in his dreams. So, because it's very important when you want to do statistics, you want to be able to understand what this theorem is about. When your population that you're dealing with is not normally distributed, which means doesn't follow the normal distribution, if you don't know this, there's just no way you are going to be able to say anything about the variables that you have, about the parameters that you have here. Due to this theorem, no matter what is the distribution, when you have the sample mean, you know that the sample mean converges to the true mean of the population, and that in general, this theorem holds. If you have x1 all the way to xn being a random sample from a distribution, it doesn't say what kind of distribution, from a distribution with mean mu and variance sigma squared, that's all you need. You just need to know that there is a mean mu and a variance sigma squared. What's the distribution? Who cares is the answer, right? As long as that is true, then the variable Wn that is defined as square root of n times x bar minus mu over sigma converges. This means converges in distribution to z, where z is the standard normal variable. When n gets large, so when n goes to infinity, when the sample size grows to infinity, the distribution of this random variable becomes bell-shaped, the standard normal distribution. So as your n grows, as you increase the number of people that you add in the study, the sample mean begins to have a bell-shaped that is centered at the true value of the mean of your population. That's what the theorem says. Okay? No matter what distribution you start with. And therefore, because of this theorem, you can build the confidence interval based on the standard normal. Because this thing grows to the normal distribution, here we say almost, it's 1 minus alpha is almost always equal to the probability that negative z alpha over 2 is less than, this is the Wn you had here, less than z alpha over 2. In Wn, you replace sigma by s, where s, if you remember, is the estimator of sigma, right? We had x squared equal, s squared equal 1 over n minus 1 sum of xi minus x bar squared, remember that? We had that and we proved that the expected value was sigma squared. That's the same s that we have here. I see some silence. Let me put you here. So s squared 1 over n minus 1 sum of xi's minus x bar squared. Okay. That's the s that we prove. S squared we prove was an unbiased estimator of sigma squared. And so that's the thing that will replace in this formula sigma. And based on the fact that this is true, now we can build the confidence interval as x bar minus z alpha over 2 times s over square root of n, and then x bar plus z alpha over 2s over square root of n. This is just one confidence interval, okay? There can be many of them. We just choose this one to be symmetric around x bar. And the probability for the true value to be inside this interval is almost 1 minus alpha, because the distribution is almost normal. So it's an approximation. You have a question on this? And this formula is used when n is large enough. So for the population that you have, any questions? An example of what I'm talking about. Assume we have a random sample of a distribution sample x bar equals 3.5 and sample variance s squared equal 1.2 for a sample size and equals 100. Now, you need to know that any other problem that you get on this topic will get down to this. You will get the data, either get the data or get x bar s squared or and the sample size. If you get the data, you compute x bar and you compute s squared. And everything else is going to follow that same work, okay? So you have two things. Either you get the data or you get the computed numbers already. If you get the data, then you compute these two numbers. And so question, construct a 95% and a 99% confidence interval. For the mean mu. So you would say, okay, the data is given. The interval, that's x bar minus z alpha over 2 times S over root n x bar plus Z alpha over 2 times S over n. This is the formula that you need to use. X bar is given, S is given, N is given. What you need to find is Z alpha over 2. So for 95%, what is alpha? 0.05, because this is 100 times 1 minus alpha. So alpha is 0.05. Therefore, alpha over 2 is 0.025. So you want to find Z.025 in your Z table. So you need to go to the Z table and you find a number that corresponds to 0.025. So anybody can do that here? You have the Z table? A 1.96. I'm asking, is that 1.96? So some of these numbers are famous. The more you use them, the more they stay, and you can just memorize them without even knowing. So that's the number. Z alpha means what? The cutoff point for the remaining probability to be 0.025. Okay? That the probability that Z is larger than 1.96 is 0.025. That's what alpha means. Z alpha means. By definition, let me put that here again, for you not to get confused when the time comes to use. So by definition, Z alpha is defined as probability that Z is larger than Z alpha is equal to alpha. Okay.
Explain how you got alpha to 0.05.
95% confidence interval is 1 minus alpha times 100. By definition of the confidence interval. So is that right here? See? So here the confidence interval is given as 1 minus alpha times 100. So 1 minus alpha times 100 is 95. What is alpha? Yes. And then from there, to put it in the formula, you know that you need to divide alpha by 2. So that's 0.025. And you go to your table using this formula to find a number such that the probability that Z is larger than that number is equal to alpha. And this is the reason why on your test I put find the probability that -3 is less than Z less than 5. Not because I need that, but for you to understand, because the rest of the class you will be doing that a lot. Going to that table to find the Z values, the T values, the high square value, and so on. An important step in that. All right, so once we found that, now we can just put in our formula. X bar is given 3.5 minus Z alpha 1.96 times S. What is given is S squared. So S is square root of 1.2 divided by N. by square root of n, and n is 100. And then 3.5 was 1.96, square root of 1.2 over square root of 100. And you, if you're happy, you can continue the computations, but for me, it's enough to write this down. Does that make sense now? You know, we together. Okay. I was happy. All right, next. That's what the example says. Now let's get back to the lecture part. The second kind of confidence interval that you can have. So that first one is in general, okay? So the first one is in general. Now, if we just when we know that the population of interest, which means the xi, x1, x2, all the way down to xn, when we know that those observations come from the normal distribution, the problem changes because of the properties of the normal distribution. So in that specific case, it is a lot better to use this other confidence interval because this is not more an approximation. This is an exact confidence interval in the case when the population of interest is normal. So the exercise tells you that the observations are selected from the normal distribution. In that case, this is the confidence interval that you're going to construct using a t instead of a z. Why? Because when you take this here, x bar minus mu over s divided by square root of whatever you have here, what you're obtaining is actually a t, a random variable that follows the t distribution, not the z distribution, exactly the t distribution when the observations are normally distributed. But when they are not, that is not more a t distribution. Okay, when the observations are not normally distributed, this is not a t distribution. And that's the reason why here, when we have this condition, this additional condition, that the data is normal, then we have the confidence interval in which we have x bar minus t, and t has here two parameters, alpha over 2 and n minus 1, which is the degree of freedom of the t distribution, and then x bar plus t alpha over 2n minus 1 s over root n. And that is true for any sample size, while this one needed the sample size to be large. In this, no matter what is the sample size, it is true because the distribution of the population is normal. On top of that, when sigma is known, because there will be problems in which it is said that the variance of the population is known, but the mean is not known. It also changes the setup. When the variance is known, you don't need to estimate something that you know, right? You don't need to estimate sigma using S because you know sigma. So in that case, you are going to replace in the formula 1, you're going to replace S by sigma in this other formula. So when the variance is known, you use this formula with sigma instead of S. Even in the case of the normal distribution. Okay. that I can do that in one problem here. To assume the data comes from normal with mean mu and variance 4. Now you know the variance is 4. It's given, so you're not going to estimate it. The sample mean is mu equals 3.1. Sorry, sample mean is x bar, right? The sample variance is s squared equals 3.4, and the sample size n equal 100 again. Construct a 95% confidence interval. For mu. And then you need to know that often, therefore, we will throw into the problem some useless information here for you to just to check if you know what you need to use in what case. So when you read this problem, you can see the important thing in the problem is the population is normal. So you know already it's normal. But on top of that, it says variance is 4. It's known. So you have to use the formula with Z, in which you replace S by sigma. So the confidence interval has to be x bar minus Z alpha over 2 sigma over square root of n, x bar plus Z alpha over 2 sigma over square root of n. And guess what? You can see that S squared is not used anyway. So again, that's the last part of the explanation where I said when the population is normal and the variance is known, even in that case, you're going to use the Z because the distribution is normal. You don't want to go and use a T when there is no T. So in this formula, there's no T, you got sigma. When you have sigma, you have to use the formula with Z. Though the problem might still give you S squared, but it's up to you now reading your problem to say, hey, the problem said normal population and variance is known, so I got to use Z. If I don't use Z, I'm doing something wrong. So you're going to drop that S squared that is given. You're not going to use it in the problem. And so here you're going to say that's 3.4 minus 1.96 times variance is 2 over square root of 100, which is 10, and then 3.4 plus 1.96 times 2 over 10. That's it. Now, does that make sense? The explanation I was giving at the end, that's what it means, that you might have a case like this, but when you know that the variance is known, then you got to use the formula with Z, in which you replace the S by sigma, because we are not using S because we know sigma. Yes. That's not why using, but we need to use 3.1 instead. Formula is clear, right? X bar is 3.1, so it has to be 3.1. Any other questions? All right, if we have no more questions, then let's look at this one, which is a little similar. The confidence interval for the proportion is going to be found the same way as the previous one. So we estimated the proportion by the sum of xi's over n, where xi's are zeros or ones, right? And we proved that the expected value of this is p. So if we want to build a confidence interval, we need to find the variance, and the variance of this was 1 over n, p times 1 minus p. So you can see we don't know this variance, so we find an estimator of this variance just by replacing p by its estimate, which is p hat. So we replace that, and we have an estimator of sigma squared. And therefore, the confidence interval in place of sigma, we put the estimator. P hat minus z alpha over 2, and then the estimator of sigma. P hat plus z alpha over 2, then the estimator of sigma. That's the general pattern of constructing the confidence interval. Whatever comes after the z is the estimator of sigma. Sigma to p hat, okay. The estimator of sigma of p hat. So that's what you would get for the confidence interval. Let's say example of that. A random experiment is conducted 200 times to estimate the probability of success in Bernoulli trials. The experiment results show 40 successes. Estimate probability of success and provide a 95% confidence interval. So we run an experiment in which you repeat the binomial, a Bernoulli random variable several times to have an estimate of the probability of success. And the question is, find an estimate and build a confidence interval, knowing that out of 200 experiments, we had 40 successes. So the answer will go as n equals 200. Number of successes is 40. That's the sum of xi's. Alpha is 0.05, which means z alpha over 2 is 1.96. You can find any other one that is requested using the z table. And so here, v hat is x over n, which is 40 over 200. That's 1/5. So your estimate of the probability of success is 1/5. And so the confidence interval is going to be 1/5 minus 1.96 times square root of 1/5 times 1 minus 1/5 divided by 200, then 1/5 plus 1.96 square root of 1/5 times 1 minus 1/5 divided by 200. That's it. As easy as hello. And the only problem you have is choose the appropriate case, get the appropriate case for the question, and bam. That is beautiful. Right. Any questions?
I have a question.
Yes.
So can you, I think I know, but can you just explain what a confidence interval is? Like, are those two values that we're saying we're 95% confident that it will fall between those two values?
This is not just two values here. This is an interval that goes from this
Right,
to that number. So including anything in between.
right.
And what this theory is telling you is that after building this interval, looking at the interval, you know that the true value of the mean, which you don't know, is inside that interval 95% of the time. Meaning what? That if I conduct this safe experiment and build the confidence interval 100 times, then 95 times, the true mean is going to be inside the interval that I built. That's what it means, actually.
Okay, thank you.
So it's not always there. That's why you have a 5% chance to miss. So if you build 100 of them with this same setup repeatedly, then 95 of them are going to cover the true value of the mean. And they are going to be different from one experiment to another. Because you can see this depends on p hat, p hat, p hat everywhere. And p hat changes from one experiment to another, right? That's why you have a chance that when you are repeating, some of them might not contain, but the theory is guaranteeing that if you do 100, 95 are going to contain the true mean. If you do 1,000, 950 are going to contain. If it's up, if it is off, it cannot be off by like 1, maybe 1, 2, but never too far from that number. Anything else? Is everybody okay with this? Now, next is what we call confidence interval for the difference of means. So we had confidence interval for the means, confidence interval for the proportion, now confidence interval for the difference in means. Meaning what? Now you have two populations, two different populations, and you want to compare their means. That's the question. Are these two means equal or not? Is one larger than the other or not? Okay. And to that end, you have a random sample, x1 all the way up to xn from one population with mean sigma square, mu1 and variance sigma square 1. You have another sample from a different population, y1 all to yn1, n1 and n2 different from another population with mean mu2 and variance sigma 2 square. And these two samples are independent. Those are the conditions, and you need to make sure you see those conditions before you start applying. Then, if that is the case, then we define the difference, the estimate of the difference as x bar 1 minus x bar 2. Why do we do that? Because we already know that we estimate the mean by x bar. So we estimate the mean of the first one by x bar, the mean of the second one by y bar, and we take their differences. So we are sure that therefore we are estimating the difference of the two means. Proof: the expected value of this is equal to mu1 minus mu2, because the expected value of x bar is mu1, expected value of y bar is mu2. So the expected value of delta hat is equal to delta. So it's a non-biased estimator of the difference of means. X bar minus y bar is a non-biased estimator of the difference of the two means. Therefore, it's a good candidate to build a confidence interval. So we find the variance knowing that these two random variables are independent. The variance is the sum of the two variances. The variance of x bar is sigma square 1 over n1. The variance of y bar is sigma square 2 over n2. That's why this is the variance of delta, due to independence. And so now, given that this is true, the random variable that is defined by the central limit theorem as delta hat minus delta over square root of its variance converges to normal 0, 1. This means converges. Right? As the sample sizes get large, it goes to the normal 0, 1 random variable, which means that we can also build a confidence interval in this setup using z by the estimate, which is x bar minus y bar from here, minus z alpha over 2 times the square root of the variance of delta hat, x bar minus y bar plus z alpha over 2 times the estimate of the variance of delta hat. That's it. And then we say again here, when sigma square 1 and sigma square 2 are known, you replace them, you replace in this formula s1 square and s2 square by the given variances. Because again, you don't estimate something that you know. If you know it, use it. Questions?
Is variance of delta hat sigma 1 squared over n1, is that minus plus times?
It's always plus.
Same
It's-
thing for in the radical.
Yes. Because it's a difference of independent random variables, so the variance is the sum of the variances, because we always do a1 squared variance of the first plus b1 squared, right? So you've got negative 1 squared. Other questions? Does this make sense today? Hmm? I sure hope so. So please. There's one last case, but I guess we don't have much more time left. So I'm not going to give you an example here. Just do that. Let's present the last case that I have here. So it's the subcase when you have the random variables coming from the normal distribution. When they come from the normal distribution and it is known that their variances are same. It's a special case when the variances are same. The problem tells you that the two populations have the same variance. But then you need to do what we call a pool variance. So you need to give an estimator of the variance that combines the two samples. Because otherwise you would have two estimators of the same value. Does that make sense? If they have the same variance and you estimate them separately, you are giving two estimators of the same variance, which doesn't make sense. So we pull all the data together and then we compute the sample variance, which is called the pool sample variance, which is obtained by multiplying S1 squared by N1 minus 1, multiplying S2 by N2 minus 1, then dividing by N1 plus N2 minus 1, and then minus 2. And you ask yourself, why this? Because in S1 squared, you have divided by N1 minus 1. In S2 squared, you have divided by N2 minus 1. So when you multiply back here, you're actually canceling the effect of that division. And the top becomes just the sum of xi minus x bar squared for everything. Now you have to divide by the degree of freedom. Here you lost 1, so it's minus 2. Because in total now you have N1 plus N2 observations, but you lost 1 degree of freedom in S1, you lost 1 degree of freedom in S2 by estimating the mean of each of them. That's why the formula gives you this. And so you are going to use this as variance instead in the formula. And that's why the confidence interval is going to be x bar minus y bar minus t, and the degree of freedom is the one that you have here, n1 plus n2 minus 2, and then sp square root of 1 over n1 plus 1 over n2, and the same thing repeating there. Why this? Because remember, the variance is square root of sigma square 1 over n1 plus sigma square 2 over n2, right? And they are all equal, so they come out of the square root. You remain with 1 over n1 plus 1 over n2, and then you have sigma outside, and sigma is estimated by sp. Does that make sense? So it's the same formula we had before, just that we took the common sigma out and replace it by its estimator, which is sp, which is common to both populations. Okay. All right. That's it for today.